In this video, we are going to talk about detectors in scanning electron microscopy. Among them, Everhart Thornley detector is a widely used detector for detecting secondary electrons. This detector not only detects secondary electrons, along with that BSE electrons can also be detected, but most widely used for detecting secondary electrons for a secondary electron imaging. This detector is named by scientists Thomas E. Everhart and Richard F. M. Thornley, based on the implementation of detectors which are found earlier. So in this lecture we mostly focus on working principle and how to maximize the detecting secondary electrons. So if we see working principle, this detector is placed inside the chamber and close to the specimen, because at the end we want to maximize the collection of secondary electrons. So this Everhart Thornley detector is like a built in the form of a tube. So if we see the second ET detector, here this is the specimen. Once the electron beam interacts with the specimen, different kind of electron signals are generated. Among them, secondary electrons and BSE electrons are most commonly used for imaging purposes, and other like X-ray X-rays also there, that is used for chemical analysis. So these for this ET detector, secondary electrons are more commonly detected by this ET detector. So once these secondary electrons coming from the specimen, and it will pass through the ET detector, and then amplification takes place. At the end, output will be come from the output coming in monitor. So now we will discuss about how this secondary electrons which are generated from the sample are collected, and how this output will be coming from the monitor. So first, this ET detector is facing 30 degrees angle to the specimen surface. Later we will discuss why this 30 degrees angle is mentioned, because at the end we are trying to maximize the efficiency of the secondary electron collection. So these secondary electrons having very low energy of about 0 to 50 electron volts. So as these secondary electrons having very low energy, so these secondary electrons have do not have sufficient energy to go to the surface of the scintillator, so that we are applying external voltage of around 200 to 300 voltage in a Faraday cage. This will attract the secondary electrons from the near to the surface to the scintillator. So here because of the using of Faraday cage, it has a few advantages, because we later we are applying about 10 to 12 kilovolts of kilovolts at the scintillator surface. This Faraday cage will prevents from the electron beam, so that damage won't be there, and also helps in attracting the secondary electrons towards the scintillator. These secondary electrons, when these secondary electrons strike the phosphorescent scintillator surface of the detector, this scintillator surface is this secondary electrons strikes the phosphorescent scintillator surface of the detector. This scintillator may be a YAG or YAP single crystals, doped light emitting plastics, lithium activated glasses. This scintillator surface is covered with a thin metal coating. Example, aluminum. Aluminum is most commonly used in this surface of the scintillator. It acts it conducts, and with a 10 to 12 kilovolts, applying a positive bias of about 10 to 12 kilovolts, so that whatever secondary electrons coming from the sample are accelerated towards the scintillator. So when these secondary electrons accelerated and strikes the scintillator, this lights will converted into lights. These electrons will converted into light photons upon striking the scintillator. Then these light will pass through the light guide. Here we can see that this is the light guide. Through this light guide, light will passes and reaches the scintillator tube. And through the light passes through the light guide and reaches the photomultiplier tube. It has quartz window which separates the scintillator detector from the photomultiplier tube. Once this light reaches the photomultiplier tube, it has a photocathode. Once this light reaches the photocathode, it has because of having low work function, because of this light, it will emit electrons. Then PMT convert back into electrons when it strikes the photocathode. So now these electrons travel in the PMT tube through the series of diodes. These diodes acts for multiplication of electrons. For example, one diode, when one electron strikes this diode, this diode will gives this diode. When this one electron strikes the diode, it will provide 2 electrons. In this way, multiplication of electrons will be takes place. This when the electrons increases, proportionally electrical signal will be there. These signals will be amplified. So output signal is further output signal is amplified by a preamplifier to increase the signal strength, so that enough signal strength will be when the enough signal strength is there, then it will be suitable for the image formation on a computer monitor. So now how can we maximize the collection efficiency of these secondary electrons? Collection efficiency of this secondary electron signal mainly depends on the position and size of the detector. This position and size of the detector. So this position is depends on the solid collection angle. Here this is phi and this is psi. This phi is between specimen and the center of the detector, and psi is the specimen to the Faraday case. Based on the experiments, found that phi at 30 degrees is optimal for collecting the maximum efficiency of the secondary electrons. And further psi is depends on A by cross sectional area of the cross sectional area of the detector to the radius r between the surface of the specimen to the detector between the length, between that length. So when the A is nothing but detector and cross sectional area of detector, it is diameter, depends on diameter. When the diameter is increases, a collection of the secondary electrons also increases. So in this way we can maximize the secondary electrons. So here in earlier we talked that ET detector can be a capability of detecting both secondary electrons and BSE electrons. And further we have applied a about minus 50 to 2 plus 250 voltage yet Faraday case. Depends on the bias voltage we applied. Collection of either SE electrons or BSE electrons can be done. Minus 50 voltage, all the secondary electrons can be rejected and only low energy BSE electrons are more effectively collected by the ET detector. So but when we apply plus 250 voltage, this secondary electrons, all the secondary electrons are attracted towards the detector and then accelerated towards a scintillator. But here along with the secondary electrons, low energy BSE can also be detected. So in this way both BSE and SE electrons can also be detected, but more widely used for secondary electrons, secondary electron imaging only, to get the maximum, to get the more resolution in imaging. When BSE electrons are combined with secondary electrons, then there will be a degradation of